Assalamualaikum warahmatullahi wabarakatuh, and hi, my name is Nurwahida Natasha binti Patra from program S245. So today I will be presenting about my final year project titled Effect of Magnesium and Titanium Doping on Nickel-Rich Cathode Materials, Structure and Morphological Studies. So this final year project was supervised by Dr. Muhammad Firdaus Kasim. Okay, for the first slide is about the introduction. So basically, over 60% of total cost of an electric vehicle battery comes from the material used, and a large portion of that cost comes from the cobalt, which is not only expensive but also linked to ethical and environmental concern. Because of this, researchers have developed nickel-rich cathode materials like NMC811 that reduce cobalt content. However, this solution brings a new set of problems, including thermal instability, structural degradation, and capacity fading. So, in my research, explores how doping on NMC with magnesium and titanium can help to overcome this limitation by enhancing its structural and thermal properties. Okay, for the next slide is about the problem statement, objective, and the significance of study. So, although NMC811 has high energy density, it has several problems, which is high nickel content causes lithium or nickel cation mixing, which can disrupt lithium-ion diffusion. And the second one is reducing cobalt, which stabilizes the structure but can lead to even more degradation. And the last one is while doping offers a possible solution, current research lacks of clarity on the best dopant types and the concentration, especially for renewable energy application. And there are a few objectives of this study, which are to synthesize the pristine and the doped NMC using co-precipitation method. And the second one is to evaluate structural integrity via XRD and the morphology via FESEM. And the third one is to assess the effect of magnesium and titanium doping on crystal structural and particle uniformity. And for the significance of study, this study is that it may help to improve battery safety and longevity, reduce dependence on cobalt, and contribute to the development of better batteries for electric vehicles and supporting Sustainable Development Goal 7. Okay, next for the literature review. So, previous study have proposed various strategies to improve the NMC811. So, based on the paper Wu, he reported 3 approaches, which is 1. Common approach is lattice engineering, where the crystal structure modified to reduce internal stress and stabilize the bulk. Alongside this, compositional tuning, where the ratios of nickel, manganese, cobalt are adjusted to minimize the phase transition and enhance the electrochemical performance. And the third one is the microstructure control, which can reduce cracking and particle disintegration during cycling. Next is transitioning from the polycrystalline to single crystal design. A study by Sun and Liu helps to eliminate grain boundaries that often serve as sites of degradation. Magnesium dopes help to reduce lithium-nickel cation mixing, and titanium dope improve the crystallinity. So, recent studies exploring on dual doping such as combined magnesium with aluminium or titanium allows better control of lattice, strain, and improve the cycling stability. And the last one is the co-precipitation method that reported by Salim is effective in producing phase pure and uniform cathode materials. Okay, for the next slide is methodology. So for this study, we use co-precipitation method followed by high temperature calcination. So first step, nickel, manganese, and cobalt sulfates were mixed in an 8:1 molar ratio. And for the doped sample, magnesium acetate tetrahydride and the titanium methodoxide were added 1%, and the pH was maintained at 11 using ammonia and the sodium hydroxide, and then filtered, dried, grind, and calcined with lithium hydroxide. And then we continue with post-annealing was done at 580 degrees Celsius to improve the crystallinity. So 4 samples were prepared: pristine NMC, magnesium dope, titanium dope, and the combination of magnesium and titanium dope. So characterization was done using the XRD for crystal structure, FESEM for surface morphology, and EDS for the elemental mapping. Okay, in this slide, I am comparing the XRD patterns of commercial NMC 811 with sample synthesis using 8 molar and 4 molar ammonia concentrations. All three samples exhibit sharp and well-defined diffraction peaks, confirming phase purity and crystallinity. And for the 8 molar ammonia sample shows slightly sharper peaks indicating higher crystallinity, while the 4 molar ammonia sample, although still crystalline, exhibits broader peaks. So this suggests slightly smaller crystallite size and possibly more internal strain or defects, but the structure remains layered and suitable for further modification. The purpose of comparing 8 molar and the 4 molar ammonia was to evaluate how ammonia concentration affects synthesis quality. So ammonia acts as complexing agents and the pH controller. The 8 molar ammonia concentration achieved the target pH faster and with a smaller volume, promoting quicker precipitation. In contrast, the 4 molar ammonia solution requires a larger volume and results in slower nucleation and crystal growth, which can promote better control and reduce cation mixing. Okay, next for the morphology for 8 molar and 4 molar, as you can see, the morphology shape is totally different. At 8 molar, it is highly agglomerate, meanwhile 4 molar less agglomerate. It is also can be noticed that 8 molar size was smaller compared to 4 molar. So at this point, we want to produce less agglomerate particle because we want to avoid the micro cracking issue that led to poor performance after repeated charge. So that is why we use 4 molar to continue the synthesis of the top sample. Okay, for the next slide is the XRD of pristine NMC, magnesium NMC, titanium NMC, and co-dope NMC. So it is shown all the samples are pure because all the P are identically the same as the pristine NMC 811. So it means all the dope samples are pure phase. And also the RIR value, only magnesium is improved because the peak at 104 much shorter than peak at 003. So this might be because of the reduce of cation mixing. Meanwhile, for the titanium and the co-dope NMC, the value is lower than magnesium. So based on all these peaks splitting, there are no issues. And for the XRD on the B is the closed up data on the peak 003. So for the dope sample, shift to a higher position compared to pristine NMC. So it is indicating that conformation of magnesium and titanium dopant successfully introduced to the lattice structure. Okay, next for the next slide is the FESEM image of magnesium dope NMC sample. As seen, less agglomerate, and it shown that the particle stands alone and tends to appear as single crystal compared to titanium and the co-dope NMC. So this improved dispersion may be due to magnesium's ability to control grain growth. So this may enhance surface stability and improve the lithium-ion transport pathway. For titanium dope NMC, we observe particles loosely agglomerate with visible gaps between grains. The structure is more open, which could improve ion accessibility, and this loose assembly could lead to the lattice strain introduced by titanium ion. And for the co-dope NMC, shows more agglomerate particle with partial fusion between grains. And last but not least, for the last characterization is the elemental mapping. So this slide is the elemental distribution whereby we can see from the mapping result and the EDX result, and as we can see, for all the sample is evenly distributed. According to the distribution of color, it is well distributed. And in the table presented here, we can see the elemental distribution, whereby proof that the existing of this dopant on NMC 811. And for conclusion, in this study, it is that proof magnesium and titanium were successfully doped into NMC 811 via co-precipitation, where XRD results shown pure and single-phase material. The second one is, among the dope sample, magnesium doping has better crystallinity, where it appears as individual crystal and has lowest cation mixing by having the higher RIR value. And the last one is that doping effectively altered the structure and morphology of NMC 811, supporting better stability. And for the recommendation in this study is that we can perform electrochemical tests for the deeper insight. Also, we can optimize dopant concentration to balance structural stability and capacity. Also, we can explore other dopant combination for further improvement. And the last one is that we can investigate the impact of doping on thermal behavior and safety characteristics. I think that's all from me. Thank you.